In this tutorial, I'll be giving a sample problem on Newton's second law with kinematics. So for this problem, it says here, a hockey puck with a mass 0.170 kilograms is at rest at the origin, x equals 0, on the horizontal, frictionless surface of the rink. At time 0, a player applies a force of 0.250 newtons to the puck parallel to the x-axis. He continues to apply this force until time equals 1.50 seconds, and then you have quite a lot of questions. We're going to be dealing with them one by one, of course. So starting with the first question, let's deal with letter A. Now take note, if you look at letter A, there are also two required to find. So you have position and speed, specifically when time is 1.50 seconds. So let us deal with position first at time equals 1.50 seconds. Let's start by writing the given. So the mass of the hockey puck is 0.170 kilograms. Next, for the force applied on the hockey puck, it says here, it's 0.250 newtons. And then for the initial horizontal velocity, it has to be 0 meters per second because as you can see, the hockey puck starts at rest. Next, the time that we are considering for part A is 1.50 seconds. So we're going to write it here. Next, the required to find is x, or position, at time equals 1.50 seconds. So this is how we write that. So let's try attacking this by looking at kinematic variables. Obviously, because position is a kinematic variable. So if you look at the given, for the kinematic variables, we have initial horizontal velocity as given. And then we're also given a specific time, which is 1.50 seconds. And what you need to solve for in this list of variables would be d sub x. Take note that solving for the horizontal displacement will tell us exactly what the position is of the object at 1.50 seconds. Although in this particular list, it's just that I opted to write displacement. But solving for this will still give you the same thing, position, because they just have the same physical significance. And then if you look at this, so you have two known variables, and then you actually have two missing variables if you look at our inventory. So acceleration is a missing variable, and then final horizontal velocity is also a missing variable, meaning to say we don't know the values of these two, but they're not what we're solving for at the moment. We're solving for position. And that's a problem because in our kinematic equations, they all require at least three variables for us to be able to use them. And we only have two known variables in here with two missing variables. What you need to do in such case is to think of what you can do with those missing variables. So example, for v sub x, it looks hopeless, but acceleration along x is actually something that you can solve for using Newton's second law. So we are given mass and force, a mass of the hockey puck and force acting on it. So we can determine its acceleration so that it won't be a missing variable anymore. So it's that simple. So going forward, let's clean the board first. And what we're gonna do for now is we're just first going to solve for the acceleration of the hockey puck within the first 1.50 seconds by using Newton's second law. So if you divide both sides of this equation by mass, since we want to isolate acceleration, you can cancel mass in here and you get to isolate acceleration along x. So this becomes acceleration equals net force along x over mass, okay? Now take note that the only force acting along the x-axis for the hockey puck is the applied force. It's 0.250 newtons. And because of that, the applied force can actually replace sigma fx in the equation. So again, nothing bloody. It's just that we are rewriting the second law equation because we want to replace sigma fx with fa, or applied force, because it's the only force along x anyway, okay? Now we plug in the given. So this is the applied force and then this is the mass. So take note that a Newton is equivalent to kilograms meters per second squared. So you can cancel kilograms in this solution. And the remaining unit for our final answer would be sorry for that. The unit will be meters per second squared, okay? So our acceleration, what you're supposed to get in your calculator is 1.47 seconds, meters per second squared for the acceleration, okay? So what do we do next? Let's go back to the required to find. So we're looking for the position when time is 1.50 seconds. So at this point, we still know initial horizontal velocity, we know time, and then we already know acceleration because we solved for it. At this point, we can solve for the d sub x, which will tell us the position at time equals 1.50 seconds because the only missing variable here is v sub x, or final horizontal velocity. Now take note, just remember that when you say, again, missing variable, that is the variable that you don't know in the problem and it's not the one that you're solving for at the moment. And the thing is you have to pick the equation which does not contain that missing variable. So pick an equation which doesn't have v sub x. That's the goal. If you look at this, the equation which doesn't have the missing variable v sub x is this equation, right? So therefore, that is the equation that we are going to use. So let's write it down. So there you go. The next thing we have to do is to is to rewrite rather d sub x using a position, because that is the exact variable that we are looking for. So d sub x is actually the change in the position of an object. So you can rewrite it as x minus x sub 0, meaning to say final position minus initial position. That is d sub x, okay? There's nothing bloody. It's just that we're replacing d sub x with the position expressions because it's the precise variable which serves as our required to find, okay? Take note that x in the equation is the one we're looking for, okay? I just made it specific. I put 1.50 seconds, but essentially it is final position and this is also final position. So they are the same thing. And what we need to do next, because we're solving for x or final position when time is 1.50 seconds, we need to transpose the initial position to the right side of the equation, okay? So this will become x equals x sub o, or final position equals initial position, plus the rest of the equation, okay? There's nothing bloody. We're just isolating x because that's the required to find, okay? The next thing we have to do, we're gonna cancel initial position because, again, if you look at the problem, the hockey puck starts at rest and the resting position is what we consider as the origin, where x is 0. So the initial position is actually 0. It's at rest. It's not yet moving. Nothing is happening yet. So you can cancel that. And then initial horizontal velocity is 0. So you can cancel this expression because initial horizontal velocity being 0, whatever is your time, you're gonna have 0 in here. And then next, the final equation would be x equals ax t squared over 2, okay? So acceleration times time raised to 2 over 2. Then we plug in the given. So this is the acceleration, and then the time is 1.50. Do not forget to raise time to the second power, and then divide everything by 2. Now, be careful because I've encountered a lot of students who would make the mistake of multiplying acceleration by time, and then they would raise it to the power of 2. That is obviously wrong. What you need to do first is, to raise only the time by the second power, and whatever you get, that's the thing you have to multiply to the acceleration value, okay? And then after doing that, whatever you get, you divide it by 2. So what you're supposed to get is 1.65 meters. So that is now the position of our hockey puck when the time is 1.50 seconds. Okay, so that is our answer for part A. So there you go, I've written it down. Now take note that we have a second required to find just for part A alone. So that is the velocity or speed of the puck at time equals 1.50 seconds. So that's it. And then for the solution, let's look at the kinematic variable. So this is our initial horizontal velocity. It's given, it's 0 at the start of the hockey puck's state, and then the time is 1.50 seconds. Acceleration is known, and then what we want to solve for is v sub x. So the missing variable, the variable that we don't know and we're not solving for, is d sub x. Wait, miss, we solved for d sub x, right? It's 1.65 meters. And that's true, but I suggest avoid using it if you can, because like what if there's an error in it, etc. So it's better to treat d sub x as a missing variable and pick an equation which does not contain it unless you really lack known variables, okay? So looking at the kinematic equations, what we're supposed to pick is the first equation because it does not contain the missing variable, d sub x, okay? Then let's write it down, but let me clean the board first. So this is our equation. V sub x equals v naught x plus axt. Or final velocity equals initial velocity plus acceleration along x times time, okay? And then next, we cancel v naught x because it's actually 0 in the problem. So we can rewrite this equation as v sub x equals a sub x times time. Next, we substitute the given. So acceleration along x is this, and then the time that we are looking at for part A is 1.50 seconds. Now, if you do that in your calculator, you are supposed to get 2.21 meters per second. So that is the velocity when time is 1.50 seconds. Okay, so we're actually done with part A. That is now the velocity when the time is 1.50 seconds. Now, let's proceed to letter B. If the same force is again applied at time equals 3.00 seconds, what are the position and speed of the puck at time equals 5.00 seconds? So let's deal with this one by one because again, we're asked for position and speed. Let's deal first with position, okay? So for you to know where the hockey puck is after 5 seconds, let's just have a visualization first of the problem because I want you to notice something. It actually skipped something in the motion of the hockey puck. So like the first part we analyzed up to 1.50 seconds, and then all of a sudden at part B we're at 3.00 seconds. So it's important to take note that this problem skips whatever happens in the middle in between 1.50 to 3 seconds. But we have to take that into consideration because we're asking for position or where the hockey puck is after 5 seconds specifically, right? So to visualize the problem, let's think of this line as the entire path of our hockey puck. And there are important points to like take note of because something happened at those points based on the information that we know. So at point A, we consider this as the 0 seconds. And up to point B, we have 1.50 seconds. And this entire trip, it covered 1.65 meters based on our part A solution. So it's important to take note of this because we're looking for the position after 5 seconds, okay? Going forward with this visualization of the problem, at point C, we're going to consider this as 3 seconds. Why are you marking the 3-second mark, miss? Because that's what we're going to analyze at part B, okay? And then up to part D, or point D, that's 5.00 seconds. So these are important points because there's something going on in between them. So this is where it covered 1.65 meters and it was accelerating at this rate. And then from point C to point D, the same force that happened in here is going to be applied again. So it's going to be accelerating from C to D again, right? And we can determine the position if we get to know the displacement from C to D, right? But that's not only that. For us to know where the hockey puck is after 5 seconds, we need to know the displacement from A to B, which we already know because of part A. Then we can solve for the displacement from point C to point D. But apart from that, we also need to analyze the part of this motion that was ignored in the problem, and that's point B to point C. So there's no information asked or there's no information given or directly asked about point B to point C, but we need to know the displacement from B to C because we're going to have to determine the position of the hockey puck when the time is 5 seconds. So that's what we're going to do first. Now, for us to do that, we're going to focus on point B to point C and solve for the displacement along X. And take note, you have to know what's happening from point B to point C. It's no longer accelerating at 1.47 meters per second squared because if you look at the problem, the net force is only applied from point A to point C, point A to point B rather, where the time is 1.50 seconds. However, the net force is no longer applied from point B to point C, meaning to say, guys, the hockey puck is no longer accelerating from point B to point C. It is obviously moving at constant velocity because if you think about it, from point B to C, the net force acting... Sorry for this. Let me erase that. Okay, so again, the net force acting on the hockey puck from point B to point C is actually 0. What does it mean? If the net force or the applied force is not acting from B to C, it means that it's not accelerating. Therefore, the velocity is constant and the equation you have to know, or you have to use rather to solve for that velocity is d sub x over time, okay? Now, the question is, what is the velocity that we're looking for? Because sure, I can solve for displacement using this. I'm just gonna rewrite it as displacement equals velocity times time because that's what comes out if you cross multiply. But what velocity do we use? Well, obviously, you have to use 2.21 meters per second because from point A to point B, it was accelerating and it reaches 2.21 meters per second for its velocity when it reaches point B. What happens after that is because there's no net force acting from B to C, the tendency of the object is to maintain whatever is its state of motion. So if it's moving at 2.21 meters per second at point B, then it will continue moving at that same speed from B to C. Okay? So that's the velocity we're gonna use to know the displacement between these 2 points. You can ignore these parts, by the way, because the initial velocity is no longer 0. It will be 2.21 meters per second, and then it's no longer accelerating, and so on and so forth. It's either these variables are not applicable or they're useless in the problem. So since this is our only equation to use, then we take this velocity as our we take this value as our velocity for this part of the problem. And then for the time, you have to use 1.50 seconds. Why? Because from point B to point C, the total time consumed is 1.50 seconds, since 3 minus 1.50 will give you 1.50 seconds. Okay, that's it. So now you can cancel seconds as the unit, and then the final answer for the displacement from point B to point C is 3.30 meters. So what? Well, you can write it there now. And again, we can go back to our actual required to find, which is the position when the time is 5 seconds. And the last thing that's missing is how far did the hockey puck travel from point C to point D. So that's what we're going to solve for. And I've revealed the given once again because these are already applicable from point C to point D. Take note that starting at point C, the net force applied in part A is applied again, same force. And then, considering that we are analyzing point C to point D, we need to update our list of given because these are not necessarily true for point C to D. Example, this is still correct, right? Mass and net force, still the same hockey puck, same net force applied, and therefore same net force applied, same acceleration, right? But the initial horizontal velocity is not 0 anymore. It will be 2.21 meters per second because, again, starting at point B, that is already the velocity of our hockey puck. So that's the initial velocity we're going to use at point C because that was maintained from point B to C as a constant 2.21 meters per second, okay? Next, for the time, 1.50 is no longer applicable because from point C to point D, the time elapsed is 2 seconds because 5 minus 3 is 2. So this will be 2.00 seconds. And then we can now look at our inventory of variables to see what equation we can use for the displacement. So as you can see, we have initial horizontal velocity, we also have the time, we also have the acceleration, and because we're solving for d sub x, we have to pick an equation which does not contain v sub x or final horizontal velocity because that's the missing variable, okay? So looking at this list of equations, what we can use is this one because the missing variable, v sub x, is not in here, okay? So we're gonna pick that, and then what we have to do is just to substitute our given. So for the initial horizontal velocity, it's 2.21. For the time, it's 2 seconds. It's just in here. And then ax t squared over 2, that's going to be 1.47 meters per second squared times 2 raised to 2 divided by 2. Okay, so we just plugged in everything in here. Just be careful because you have to square only 2 seconds, only the time. And then after squaring time, multiply it by acceleration, then divide whatever you get by 2, and then add that to the product of 2.21 and 2 seconds, okay? What you're supposed to get in here is 7.36 meters. So that is now the displacement from point C to point D. So what are we going to do next? Since we're solving for the position of the hockey puck after a 5-second interval, what we have to do is just to add all those displacement values from point A to point D. So that would be position after 5 seconds is 1.65 plus 3.32 from point B to C, and then from point C to D, so 7.36 meters. So nothing bloody, we just added all the individual displacements covered within those 3 different time intervals. Okay, so that is the final answer, 12.33 meters, which looks sensible because there's enough time, there's enough space for a for that displacement to like happen in a ice skating rink. So that's it for the position. For the final required to find in letter B, that's the speed of the puck at 5 seconds. So we're going to focus again on point C to D and look at our given. So if you look at the given, we have initial velocity, time, and acceleration. So if you want to solve for the velocity, final velocity at 5 seconds, we can use this. So see, you have the initial velocity, acceleration, and time. So we're going to use that to solve for our v sub x or final velocity. Okay, so that's our equation. Then we just plug in the given. Initial horizontal velocity is still this. That's 2.21 meters per second. And then acceleration times time would be this. And then what you're supposed to get is 5.15 meters per second for the velocity at 5 seconds. So that's it. The problem looks complicated, but not really. This is just a combination of constant velocity kinematics and uniformly accelerated motion. You just need to be careful in problems like this because like the case where, they skip point B to point C, but you have to solve for it because you need to know the overall change in the position of the hockey puck, considering the 5-second interval, and the problem did not care about B to C, but yes, we still had to, we still ended up having to solve for the displacement in there because it's needed for us to know how far the hockey puck really traveled from 0 second to 5 seconds. Anyway, so that's all for this video. Thank you so much for watching. Anyway, this is the summary of the answers for part A and B. So have a great day.